Welcome to this video. My name is Arpit Singh, and in this video, we are going to see solution of end semester examination question paper of numerical analysis design. Let's see the questions. In the first question, we have given a nonlinear equation x square minus x minus 1 equals to 0. We have to apply various numerical methods to find its root. For any one of the numerical methods, bisection or fixed point, perform the following task. Described as a algorithmic step to present a flowchart for the method clearly indicating initial condition or assumption, iterative formula or rule, stopping criteria, numerical results. First, we have to create a flowchart for the chosen method. In this video, we are going to choose bisection method, clearly indicating these tasks. Draw the flowchart for iterative calculation step by step, tabulate intermediate results such as current approximation, function value, and error at each iteration. We also have to create a flowchart for our chosen value. Geometric interpretation, we have to create a graph illustrating how method approaches its root. Estimate the error at each step, absolute or relative, and demonstrate the convergence behavior and order of convergence of the method. First we see algorithm for a bisection method. Start the algorithm, define the function fx is equals to x square minus x minus 1. Input the interval ab such that f a into fb is smaller than 0, because we have to take negative and positive value from so that the root lies in between them. Input the tolerance e, which is error limit. Repeat until the error is less than epsilon, error limit. Find mid a plus b by 2. If f of mid is equals to 0, then root is found, return mid. Else, if f into a into f of mid is smaller than 0, then set b to mid, or else set a to mid. Print mid as the root approximation, then stop. This is the algorithm for bisection method. This is the flowchart of bisection method. First we start, then we read a, b, the value of the function in which the one is negative and one is positive, and epsilon, the tolerance value. While b minus a is smaller than epsilon, mid a plus b by 2, this flowchart shows if f of mid is equals to 0, then we have found the root, or else we have to check if fa into fb is smaller than 0, then set b is equals to mid or a is equals to mid according to that, and repeat the while loop until we find the root. This is the graphical interpretation of the function. Here it is like a parabola in which fa, f2, f3 are positive values, and fb, f1, fb2, fb1 are negative values. Here lies the root of the root of the function. Error at each step is b minus a by 2. As iteration increases, error halves. This show the linear convergence of the bisection method. Bisection method has order of convergence 1, that is slow but guaranteed convergence. Bisection method may be slow, but it always guarantee that the function will converge. Question 2 is consider following data points 5, 157. These are the values, like 5 is the value of x, and 150 is the value of y. So 5, 150, 7, 392, 11, 14, 52, 13, 23, 66, 17, 52, 02. Using Lagrange or Newton interpolation formula of finite differences, estimate the value of the function at x is equals to 9. For the chosen interpolation method, perform the following task. In this video, we are going to see the Lagrange interpolation formula for solving this question. Describe the initial assumption or preconditions, that is number of data points, form of the interpolation polynomial. We have to describe what are the preconditions we have taken solving these questions. The general formula, recurrence relation used in the method, any stopping criteria if applicable based on desired polynomial degree. Compute the value of f9 using the polynomial. Compare the interpolating polynomial with actual data points on graph. Error estimation, absolute or relative. We have given 5 data points, 5 1 n. So the Lagrange formula is fx summation of I to 0 to n. and pi of j to 0 to n x minus xj by xi minus sj. This is the Lagrange formula. Using the formula, we can find the value of f9, which is equals to 180. The plot graph interpretation of Lagrange interpolation is that given data points are exponentially gives value exponentially. This is the graph of Lagrange interpolating value, and f of 9s give the value of 810. The method of error approximation in Lagrange interpolation is the exact function is unknown, so no value of f of 9 to compare. But the interpolation is smooth and 9 is within the range of known values, so there is low error likely. The formula of relative error is mod of f actual minus f9 divided by mod of x actual. Question, question number 3 states that we have given the following set of data points. These are the value of x and with the value of y. Using suitable numeric differentiation technique, estimate the first and second derivative of the function at x is equals to 9. Describe the algorithm or provide a flowchart for the interpolation based differentiation process. We have to give algorithm or this flowchart for this process, present intermediate result and final value of the derivative, estimate the error in derivative if possible. The algorithm is like we have to take input of data points x0, y0, x1, y1, x and yn and construct Newton's divided difference table, in which we have to calculate first divided difference f x0 x1 is equals to f x1 minus f x0 divided by x1 minus x0. This is the formula of calculating divided difference. And then we have to keep building higher order divided differences. Then we construct Newton's interpolating polynomial px and then differentiate px symbolically or term by term according to the polynomial. Then we evaluate first and second derivative of px at x is equals to 9, then output the results. The data points are f157, are 5, 157, 392, 11, 14, 52, 13, 23, 66, 17, 5202. So the value of f dash 9 comes to be 320.16 and f double dash 9 comes to be 68.67. The error depends on higher order derivatives of the true function. Since we don't know the actual function, we cannot compute exact error, but we can estimate it by this formula of the error. Question number 4 is obtain formulas for numerical quadrature and obtain Simpson's rule from it. Write algorithm form for Wedel's rule. The numerical quadrature refers to approximating definite integrals by evaluating the function at specific points and weighting these evaluation. The general quadrature formula is integration a to b fx dx summation where I is equals to 0 to n wi dot fxi, where xi are sample points interval a b, wi are assigned weights to each point, n is the number of points used. The derivation of Simpson's 1 by 3 rule from quadrature. We take 3 points where x0 is equals to a, x1 is equals to a plus b, x2 is equals to b. We approximate the function fx by a second degree polynomial, that is a parabola over the interval ab. Divide the interval into two equal parts, giving us these 3 points. Using Lagrange interpolation for a quadratic polynomial and integrating the interpolated polynomial over ab, we obtain integration fx dx from a to b, that is approximately equals to b minus a by 6 fx0 plus fx plus 4fx1 plus fx2. This is called Simpson's 1 by 3 rule. Then the algorithm for Wedel's rule is this. First we see Wedel's rule formula. If the interval AB is divided into 6 equal subinterval of width h, the Wedel's rule states that integration fx from a to b is equals to 3h by 10 f0 plus 5 f1 plus f2 plus 6 f3. plus F4 plus 5, F5 plus F6. The algorithm for this is we take input function x, fx, limits a, b, and number of intervals n. The n must be multiple of 6. Then we compute step size h is equals to b minus a by n. Initialize total integral I is equals to 0. For each group of 6 subinterval, that is every 7 point, we compute x0 is equals to a plus I dot h, x1 is equals to x0 plus h, and so on. X6 is equals to x0 plus 6h. Then we evaluate respective function for this. F0 is equals to fx0, f1 is equals to fx1, and so on. Then we compute partial integral 3h by 10 f0 plus 5f1 plus f2 plus 6f3 plus f4 plus 5f5 plus f6. And we add this to the total partial integral to the complete integral and repeat this for all intervals, then print the final integral value I. Question number 5 is write algorithm for computation of Gaussian quadrature formula for n is equals to phi, and we have to evaluate phi from this integral. Algorithm for solving this is we have to input function fx and limits ab, then convert integral from ab to -1 to 1 using change of variables. The change of variables can be done using this formula x is equals to b minus a by 2 into t plus a plus b by 2. For n is equals to 5, we use standard nodes xi and wi. We compute integral by b minus a by 2 into summation I is equals to 1 to 5 wi into f and the change of variables. Then we output value of I and of the algorithm. Approximation of pi can be done using this formula in which we convert -1, we convert limit 0 to 1 to -1 to 1 using change of variables as explained, and we can use Gaussian quadrature formula, which results I is approximately equal to I minus 1 minus 0 by 2 into summation of I is equals to 1 to 5 wi into f into 1 by 2 xi plus 1 by 2. If you evaluate using above value, the final result is approximately 3.1415926, which is very close to the value of pi. Question number 6 is apply pivoting and solve given system of linear equations using any direct method. Here three equations are given in which we have to find the value of x, y, and z. First we create a augmented matrix A which contains data from this equation. The largest value in column 1 is 3, which is in row 2, this value. So we swap row 1 and row 2, creating this matrix. We then make the element below pivot in R2 is equals to 0. So R2 becomes 0, 4 by 3, 8 by 3, 32 by 3. We then make sure the element below pivot in R3 is equals to 0. Then we use multiplier for R3, which is 2 by 3. So R3 becomes 0, 5 by 3, 4 by 3, and 34 by 3. The new matrix become like this. Then we use multiplier 4 by 5. So R3 becomes 4 by 5 into R3 becomes R3 minus 4 by 5 into R2. Then we compute first element as 0, third element as 8 by 5, and RHS equals to 8 by 5. So new matrix become like this. We can then calculate from row 3 that Z is equals to 1, from row 2 that Y is equals to 2, and from row 1 that X is equals to 1. So the final values of X, Y, Z in this matrix are X is equals to 1, Y is equals to 2, and Z is equals to 1. Question number 7 is write algorithm for best iterative method from below and give output from question 6. The question 6 that we have done previously, Jacobi iteration method or Gauss-Seidel iteration method. Gauss-Seidel iteration method works by having three or more equations. Then we rearrange equations to solve for each variable, that value of x, y, and z. We initialize guesses x0, y0, and z0. For example, all 0, then we repeat for n iteration or until error is smaller than tolerance. X to the power k plus 1 is equals to f x k y k z k, y to the power k plus 1 is equals to x k plus 1 y k z k, z to the power k plus 1 is equals to f x plus 1 y k plus 1 into z k. We stop when mod of x k plus 1 minus x or mod of y k plus 1 minus yk or mod of z k plus 1 minus zk are all three below of tolerance, which is epsilon. First we take x0, y0 and z0 to 0, solving the earlier given equation. In iteration 1 we get z1 is equals to 10, iteration 2 is in which we get z2 is equals to 20. Gauss Seidel, here we can see that the values are not converging. Instead, the values are diverging. So Gauss Seidel is not a good choice here because the system is diverging. We try Jacobi method instead since Gauss Seidel diverge. We use same initial guesses. And equation was x1 is equals to 14, y1 is equals to 5, z1 is equals to 7. In iteration 2, x2 is equals to minus 17, y2 is equals to minus 19.5, z2 is equals to minus 14. Jacobi method is also diverging. This system is not suitable for iterative method due to lack of diagonal dominance. The system we have given is very less diagonal dominance, since we cannot use iterative methods to solve this. Question number 8. Write algorithm for Runge-Kutta method and give output for ordinary differential equations. We have given a differential equation dy by dx is equals to 1 plus x plus y, in which y0 is equals to 1 it is given, and we have to find y1 in steps of 0.25. The algorithm for Runge-Kutta method is find the defined differential equation fxy is equals to 1 plus x plus y. Input initial conditions x0 is equals to 0, y is equal to 0 is equals to 1, and step size 0.25. Repeat the following steps until x is greater than equals to xf. First we compute k1, k2, k3, k4 with these formulas, and then we update y n plus 1 according to the found k1, k2, k3 and k4 with this formula. We update n plus 1 as xn plus h and output yh each step. This way the algorithm of Runge-Kutta method works. We have defined we have given that fxy is equals to 1 plus x plus y, fx0 is equals to y0, y0 is equals to 1, and h is equals to 0.25. We have to find y1. We calculate for x 0.25, 0.5, 0.75, 0.1.0. In step 1, we calculate for 0, x is equals to 0 and y is equals to 1. We calculate f01, which is 0.5. We calculate f01 and replace f0.125 and replace it by 1.0.5 by 2. So it results in 0.59375. Then f0.125, 1 plus 0.59375 by 2 results in 0.60546875. Then f0.25, 1 plus 0.60546875 results in 0.7138671875. These are the values of K1, K2 and K3, K2, K3 and K4 respectively. We then compute y1 by using these values of K1, K2, K3, K4, which comes to be 1.60205. We then repeat the same method. Then the values of K1 is 0.7130125, K2 0.83338906, K3 0.84843613, K3 K4 0.987625153. The value of y2 becomes by this K1, K2, K3, K4 2.44610. The value in step 3 we take x is equals to 0.5 and y is equals to 0.244610. Then value of k1 is 0.986525, k2 is 1.61698884, k3 1.204596, k4 is 1.429674. The value of y3 then comes to be 3.6217. In step 4, we take x is equals to 0.75 and y is equals to 3.6217. So value of k1 is 1.568, k2 1.868, k3 1.905, and k4 2.265. The y4 then, after computing the value of these k1, k2, k3, k4, y4 gets to 5.2555. The final answer, as it has it has less order than order of convergence, the final answer becomes y1 is equals to 5.2555. This is the explanation of end semester exam question paper. Thank you for watching.